Yes, is my screen visible?
Yes,
Yes, sir.
Okay. So we will continue now. So last time we have studied the Rayleigh Ritz method, and in the previous class we have gone for the point load, that is the concentrated load. So today also we will continue with Rayleigh Ritz method, that is RAYL Rayleigh Ritz method. Okay, and today we will try to cover a problem in which the surface loads are there in the given in the problem. Okay, so I am directly jumping to the problem now. Okay, so what I'll do, let us consider a simple bar like this. Okay, so we have a simple bar which is like going like this. Okay, and we have a fixed support over here. Okay, so it's a bar, it's not a beam, it's a bar. Okay, and what we do, we assume here this is your x-axis, and this point will be your origin, so this will be having 0 coordinate. Okay, now let us consider the length of this beam or this bar as L meters. Okay, so this is the length of the beam, length of the bar. Okay, we are assuming the area, okay, and E as constant. Okay, so this will be constant. Okay, now in the previous class point load was there, but for this case, today's case, we will be having a kind of a UDL or maybe a surface load. We can call it as a surface load. Okay, so if you draw the surface load, it will look like this because it is acting in the direction of the x-axis, so it is acting like this. Okay, so now it is shown in this particular pattern. Just for sake of example, if you take a simply supported beam like this. Okay, so what we have a load which is like this. Okay, so this is nothing but a UDL. Okay, so this is a UDL which is acting on the beam, right? Now what will be the UDL value over here? This will be a constant value, so this W will be some value, maybe 10 kilonewton or so and so. Now you see here this load is acting, if you consider this as a beam, so here this is your x-axis, this will be your 0 axis. So basically in this case the load is acting perpendicular to the x-axis. But as far as this problem is concerned, so in this problem, in place of acting the load is acting in the perpendicular axis, it is acting in the direction of the axis. Okay, so this is the difference. So this is a surface load which is acting in the direction of the axis. Okay, now if I take the similar example over here, let us say if I take same beam which is like this. Okay, so we have a simply supported beam, and here we have a triangular load. Okay, so if I consider this as a triangular load, in that case what will happen, let us say this is 10. Okay, and the length of this beam is, let us say, L. Okay, so what is happening over here is, as this if you consider any section, let us say this is section XX, so if the section is moving in this direction, the amount of load is continuously increasing. Okay, so if I want to know the value of W, so W can be treated as some constant A into X. Okay, so why I'm saying this some constant A, because constant will be there, and as the value of X is changing, let us say if X value is 0. Okay, so if this is 0, this W will be also 0. So we are at this point, so this value will be 0. So if X value is L, so this W value will be something like 10. Okay, so this is a simple representation of a triangular load on the beam which is over here, right? So now here also in our problem also, I'm going to consider this as a triangular load. Okay, and its value is P equals to some constant C into X. So basically what is happening over here is, if your x is 0, so let us say I am at this point, that is at the fixed support, so the value of load is 0. But as you move away from the support, okay, as your x is changing, your p value is increasing, and p value is maximum when you reach at this section. Okay, so this is the meaning of this. So this is very much similar to your triangular load, but in place of acting in the direction of perpendicular to the axis, it is acting along the axis of the geometry of the beam. Okay, so now this is how we are going to define the surface load. A typical example of the surface load is pile. Okay, so if you consider a simple pile over here, let us say we have a ground. Okay, this is your ground, and here you have a pile which is inserted in the ground. So if you apply a force over here, so what you will get? You will get a reaction from the surface, isn't it? Because of the cohesion between the soil and the surface of the pile, which is usually concrete pile. So there will be a cohesion, and because of this, along the periphery of the pile, there will be a force which is generated, and that force will be called as a surface load. Okay, so this is very much similar to the case which we are dealing over here. Okay, now how to solve this problem? Okay, so what we have learned till now, that we have to find out the total potential energy, that is total potential energy equals to, I think I have made some spelling mistake over here. Okay, so this is total potential energy is nothing but the strain energy, okay, plus work done, isn't it? So usually what we write, this total potential energy, usually it is denoted by symbol pi. Okay, so this pi is strain energy is U, plus work done is generally denoted by W. Okay, so in the previous class we have seen the equation for the strain energy. Okay, strain energy is equals to, so we can write over here something like U equals to, in the previous class we have seen it is A E divided by 2 integration over the length, and here we have something like du by dx whole square into dx. Okay, so now for this purpose, in order to calculate the strain energy, you should know what is the value of U. Okay, and if you remember correctly, we have to assume this value, isn't it? So we have to assume this. So let us start with the problem by assuming the displacement polynomial with some equation. Okay, before that, let me write down the work done equation also. So this is work done. So usually this work done is denoted by a symbol something like W. Okay, capital W. So it has got three components: W, that is point load, okay, plus W, that is surface load, plus W, that is the volume load. Okay, now in our case, this part, that is point load, is not at all there, volume load is not at all there, only the surface load is there. And if you remember in the previous class, we have seen the value of W for surface load can be calculated as integration over the surface, then we have U transpose into Fs, that is the surface load, and it has to be integrated over the surface, where this U, okay, U transpose is nothing but the same one, the which we are going to assume over here. Okay, so now let us go for the solution of this particular problem, and for this purpose, let me write down the equation. Okay, so we are going to consider this as case 1. Okay, so now in the case 1, what I'm going to do is I'm going to assume, that is let me write down over here, that is assume the value of U. Okay, so the value of U can be written as something like U equals to something like A0 plus A1 times X. Okay, so this is the same polynomial which we have assumed in the earlier class. Okay, So this is one of the basic or the simplest polynomial for displacement function. Now our aim over here is to find out these unknowns, that is a0 and a1. Okay, so for this purpose we have to apply the boundary condition. Okay, but before applying the boundary condition, let me draw the free body diagram. Okay, so this is a simple free body diagram over here. So now I am going to call this as point number 0 and this will be point number 1. Okay, so this is point number 1, right? So if I consider this as origin, okay, so this is my origin, this will be my x-axis. So in this particular case you have this coordinate. So here the x coordinate will be called as x0 and its numerical value will be 0, and here x coordinate will be called as x1 and its numerical value will be L. Why L? Because in the problem the value of length of the beam is given to you in terms of L only. Okay, now secondly, if you talk about the displacement, so displacement at this point u will be called as, let us say, u0. Okay, and here the numerical value of displacement is 0. Why it is 0? Because at this end there is a fixed support, so the value of displacement at this point will be 0. If you talk about the other end, so here u will be called as u1 because this is node number 1 and we don't know its value of unknown displacement. Okay, it's a simple unknown thing. Okay, so now with this much of information, let us now apply the boundary condition. Boundary conditions. Okay, so if we apply the boundary condition in this particular case, we will have to slightly go down. So here we will say at point 0. Okay, so at point 0 the value of x is x0, the numerical value is 0, and the value of u is called as u0 and its numerical value is also 0. Okay, so what displacement function we have assumed? That is u equals to a0 plus a1 times x. So I'm going to substitute these values over here. So u will become u0 and its numerical value is 0. A0 is unknown, so I'm going to keep the same thing. Then a1 into x. So x here it is nothing but x0 and its numerical value is 0. So if you solve this, you are going to get a0 value as 0. So ultimately what is going to happen over here? The displacement polynomial which we have assumed, that is now reduced to something like a1 into x. Okay, I hope this is clear to you. So this is a1 into x. So now in order to calculate the strain energy, so I need to have du by dx. Okay, so you already have the value of u. So from this I can easily calculate du by dx, that is d by dx of a1 into x. So if you solve this, what you are going to get is only a1. Okay, I hope this is clear to you. So now based on this information, let me calculate now the strain energy. Okay, so the strain energy, like I said earlier, this is denoted by a symbol capital U, and this is A E divided by 2 integration over the length. So this is du by dx whole square into dx. Okay, so if you solve this, right now the value of A is constant, value of E is also constant, it is given in the numerical, and this is integration over the length. Now du by dx is nothing but now your a1, this will be whole square into dx. Okay, so now what is going to happen over here? This is ae divided by 2 and this a1 square will come out, and this is integration over the length and this is dx. So again if you solve this, so what you are going to get? So integration over the length of dx is nothing but x, and if you put the lower limit and upper limit, so you are going to get this as L. So finally you are going to get AE L A1 square divided by 2. So this is nothing but a expression for the strain energy. Okay, now coming to the work done part. So let me write down over here. Okay, work done. So usually this work done is having 3 components. Just now we have seen, out of which only one component is there in this case, that is the surface load. So this integration will be now over the surface. This is U transpose into Fs over ds. Okay, so now what is my U transpose? Now just now we have seen this is the expression for displacement. Okay, that is U equals to A1 into x. Okay, so I am going to put the same expression in the integration part over here. So here the again I have missed this negative sign because in the yesterday's class, if you remember, the work done has to be taken as negative. Okay, so this will be negative. So here I am going to put U transpose. So A1 into x, it's a simple 1 by 1 vector, or 1 by 1 element is there, so its transpose will be exactly same. So here I am going to write down something like A1 into x. Okay, now Fs is your surface load. Okay, so the value of Fs is given in terms of x. Okay, it is given in the problem itself that this Fs is nothing but your P, and its value is nothing but C into x. Okay, so this is given in the problem. So here I'm going to put I'm going to substitute over here, that is this is C into x. Okay, so this is the surface load over ds. Okay, so now this will be of course integration over the surface. So here the expression will be something like over the surface, and here if you go for the multiplication, so you will have something like C, we have A1 into x square over ds. Okay, so now if you take out these constants outside, so C is constant, your A1 is constant, negative will be there, and here you can write something like S into x square over ds. Okay, now you see this is integration over the surface, right? So you just imagine that this is a bar. Okay, let me draw a bar over here. Okay, so this is a bar. Okay, so how you are going to get the surface of this bar? Okay, so if this is a circular bar, so your surface will be something like the length, okay, multiplied by the circumference, isn't it? So if you consider the cross section of this bar is like this, so your surface, that is this particular surface, okay, so this surface can be calculated by simple multiplication of length into circumference. Okay, so now this circumference is not given to you, okay, because even the shape is also not given. It can be even a rectangle also. So what we are going to assume over here, this circumference value is unity. Okay, so this will be nothing but 1. So now your surface is going to become length. Okay, so if you do this, so the same expression now can be written as C into A. Now in place of S, that is surface, we are going to put L over here. We have got x square. Now ds will be now becoming ds into 1. Why 1? Because we are going to take the other dimension, that is the circumference dimension, as 1. So finally you can rewrite this expression, that is W as minus C A1 integration over the length, and you have x square into dx. Okay, so if you solve this, so integration of x square is nothing but x cube divided by 3, and this will be integrated over the length. So this will be minus C A1, and this will be x to the power 3 divided by 3. This is ranging from 0 to L. Okay, so this is nothing but L cube divided by 3. So finally your work done value will be something like minus C A1 L to the power 3 divided by 3. So let us call this as expression number 2. So this is the expression for work done. So now you have this expression. This is for strain energy, and this is for the work done. So now what we can do, we can have the potential energy. Okay, so let me write down this total potential energy. So if you remember, this total potential energy, generally it is denoted by a symbol pi, and pi is nothing but the strain energy plus work done. Okay, so if you refer the earlier section, your strain energy is AEL A1 square divided by 2. Okay, so let me write down that. So this is something like AEL A1 square divided by 2. okay, and your work done is nothing but negative C A1 L to the power 3 divided by 3. So this is the total potential energy pi. So now if you see this total potential energy content, everything, all the values are known except A1 value. Okay, A1 value is a constant which we have assumed and we don't know its value. So what we can do is we have to just go for the equilibrium conditions, and in the case of equilibrium condition, the total potential energy is 0. Okay, or rather minimum, not 0, it should be minimum. So for this purpose, what you can do is you can go for a partial derivative of total potential energy with A1, and this should be equated to 0. So here we can write the same thing, that is AE L divided by 2. This is del by del A1 of A1 square minus we can have C L to the power 3 divided by 3 into del by del A1 of A1. Okay, so if you analyze this, so what you are going to get over here is something like A E L upon 2. So this will be 2 times now A1 minus this will be C L to the power 3 divided by 3, and this will be gone. So this will be treated as unity. Okay, so finally this has to be equated to 0, isn't it? So final expression will be something like this, that is A E L. So this 2 and this 2 will be cancelled. So this will be A1 equals to, sorry, not equals to, it should be minus this will be C L to the power 3 divided by 3. So this minus sign will go over here. So now you have C L to the power 3 divided by 3 equals to A E L A1. So you can solve this for A1. Okay, so finally the value of A1 can be calculated as C L square, okay, divided by 3 times A and E. I hope I am right. Okay, so this is, let us say, expression number 3. So is it okay, students? Everybody, is it fine?
Yes, sir.
All right. So we know the value of A1 now, and if you refer the earlier section, so you know the value of U, which we have assumed earlier. So we have assumed the value of U as U equals to A0 plus A1 into X. So finally A0 was 0, and we came to know that U is now only A1 into X. And now we know the value of A1. So your displacement polynomial, so U will be now A1 into X. So we can substitute the value of A1 over here. So this is C L square divided by 3 times AE into X. Okay, so this is the expression for the displacement. Okay, so now let us try let us try to plot the variation of displacement across the length. Okay, so for this purpose, what I'm going to do is I'll just draw a simple straight line over here. Okay, so this is my straight line, right? And this is my 0, and this is my L. Okay, so now in this expression, okay, so I'm talking about this expression. So in this expression, if I substitute the value of X as 0, so if I substitute the value of X as 0, you will get here the value of displacement will be 0. And since there is a fixed support over here, so it has to be 0 over here itself. Okay, but now if you substitute the value of X over here as L, I'm talking about this point now. Okay, I'm talking about this point. So here the value of X will be L. So the entire expression will become something like this. So this will be C L to the power 3 divided by 3 times A into E. Okay, now you see this is a single degree polynomial. So what we can do is we can simply join with the help of a straight line over here. So you can see that as the value of X is changing, your displacement is continuously increasing, and the maximum value of displacement will be there as CL to the power 3 divided by 3 times AE. Okay, so this is the variation of the displacement. Now let us see the strain component. So if you calculate the strain, so strain is nothing but du by dx. Okay, so if you go for derivative of this particular expression, So this will be something like C L to the power 2 divided by 3 times A into E. There is no X component over here. Okay. So this X component will be completely gone. So this is nothing but a 1 over here. So what is the meaning of this? The meaning of this is like this. So if you draw a variation of strain now, so if irrespective of your X, so your X value is 0 over here, X value is 1 over here. So now you see, since there is no X component present over here, so even if you calculate the stress at this level or maybe at this level, so the stress will be constant, that is C L square divided by 3 times AE. Okay, and this will be this will be CL square, not 3L square. So this is CL square divided by 3 times AE, and it has to be joined with the help of straight line. Okay, so all I'm trying to say over here is this strain component is constant, okay, irrespective of the position of the point. Okay, just a moment please. I think, yeah. So irrespective of the point, you will get this strain as a constant value over here. Okay. Similarly, if you go for the stress, so how you are going to calculate stress? That is E into strain. So the same expression will come over here. Only thing is the E will be gone. Okay. So this will be E into CL square divided by 3 times AE. So this E will be gone. So your stress will be something like C L square divided by 3 times A. So in this component also, in this here also, the X component is not at all there. So what is the meaning of this? That is, the irrespective of the location, you will always get a stress as a constant value. Okay. So here you will have a constant value. Here also you will have a constant value. Here X will be 0. Here X will be L. Okay. Here this should be L. Okay. And the value of the stress will be C L square divided by 3 times A1. Here also this is C L square divided by 3 times A. Okay. Not sorry. This is not A1. This is only A. Okay. So you see, if you consider this polynomial, so I'm going back over here. So if you consider this polynomial, that is U is equal to A0 and A1 plus X. So what you are going to get is this one. So this is the variation of displacement. This is the variation of strain. This is the variation of stress. Now you just understand that the stress is constant throughout the length. Okay. If there is a point load which is acting at the end of the bar, in that case the stress should be constant. Okay. But if you see the type of loading in our problem over here, so you can see the in this problem the type of load is continuously increasing. Remember, this is a function of X. So here the load, so if you put the X value as 0 over here, so at this point the value of load will be 0. If you put the X value somewhere, something like L by 2, so here you will have P value as C into L by 2. And at this point, if you substitute the value of X as L, so your P value will be C into L. So as the length is increasing, your force is also increasing. Now, since the force is increasing, you cannot have a variation of stress as a constant. Okay. So your stress will never be a constant. And what you are getting over here, your stress is continuously constant irrespective of your location. So the meaning of this is, whatever you have done till now, it is not correct. And why it is not correct? Because you have assumed a polynomial, something like this, and this polynomial is not good enough to give the appropriate results. Although it is giving you results something like this, but these results are not matching with the actual type of a problem. Now, how to deal with this problem? So if you remember, in the previous class also, we have found out that the solution of the problem which we have solved using that simple expression, it was not giving us the correct solution. So now in that case, we have gone for the higher order equation. So in this case also, we may have to go for the higher order equation. Okay. So is it okay to everybody till now? Somebody please respond.
Yes, sir.
Okay. So now let us try and solve the problem, same problem, with the help of higher order equation. So here now I am going for the case 2. Okay, so let me write down over here. This is CASE case 2. Now in the case 2, what I'll do, I'll use the value of u, okay, as a0 plus a1 into x plus a2, oh sorry, this is plus a2 into x square. So one order I have increased, right? Now let me draw the free body diagram one more time. So this is my free body diagram over here. Okay, let me consider this as origin and this as your x-axis. Okay, so if I consider the number of points, so this is point number 0. Okay, let me call this as 0, and this is point number 1. Okay, so here if you substitute the values, so here x will be called as x0 and its value will be 0, and here x will be called as x1 and its value will be L, because the length is given over here, the length of the bar is given as L. Similarly, if you consider the displacement, this will be called as u0 and its numerical value is 0 because there is a fixed end over here, and here this will be u will be called as u1 and its numerical value is unknown. Okay, so I'm going to put a question mark over here, right? So now let us apply the boundary condition. Okay, so now if you apply the boundary condition, so let me apply the boundary condition at the first point. Okay, let me slightly go down. Okay, so at point 0. Okay, so at this 0 point, what is happening over here, that is x will be x0 and its numerical value is 0. Similarly, u is called as u0 and its numerical value is 0. Okay, so the expression which we have assumed, so same expression I am going to write down over here with the help of values. So now u is called as u0, its numerical value will be 0, so this will be a0 plus a1. What is the value of x? X is nothing but x0 and its numerical value is 0 over here. Then a2, then x value is also 0 over here. So if you solve this, what you are going to get is a0 as 0. Okay, so finally this expression will become now u equals to a1 into x plus a2 into x square. Here square should be there. Okay, so now I am going to apply the boundary condition at the second point. Okay, so here I'll say at point number 1. Okay, so at point number 1, x will be called as x1 and its numerical value is L. Similarly, u will be called as u1 and its numerical value is not known. Okay, so we'll keep only u1. So this value of displacement, it will be something like this now. Okay, so if you write this, so here this u is nothing but u1. We don't know its value, so we'll keep u1 only. So we'll call this as a1. X value is nothing but L plus a2 into you have now L square. Okay, I hope this is correct. Okay, so now what we can have is a simple expression wherein you can have a relationship between u and a in terms of L. Okay, if you remember, we have to go for the derivative of u also. Okay, so if this is u, so I am going to write down something like u, or rather I can go for du by dx here itself. Okay, so du by dx can be calculated as, here you will have something like a1 plus this will be 2 times a2 into x. Okay, is it correct, everybody? Barabar hai hai?
Yes, sir.
So this is du by dx. Okay, so you just imagine that this is your final expression of u, and this is the final expression for du by dx. Okay, so now let us quickly calculate the strain energy. Okay, so let me write down over here strain energy. Okay, so your strain energy can be calculated over here as u equals to a e upon 2 integration over the length. This is nothing but du by dx whole square into dx. Okay, so now I am going to write down the expressions now. So a and e, they are constant. There is no change in length and the modulus of elasticity of the bar. So this will be ae by 2. This will be integration over the length. Your du by dx, so du by dx is nothing but a1 plus 2 times a2 into x. This is a whole square term. Okay, so now we have to go for the square of this, and we have to go for integration also. Okay, so let me write down this first. So this is ae divided by 2 integration over the length. So here this term will be something like a1 square. Okay, so this is 2 times this and this, so this will be 4 times a1 a2 x. Okay, plus the square term of the last one, so that is 4. This will be a2 square as well as x square into dx. Okay, so now all we have to do is go for the integration of this. So let me write down over here. So this is a e divided by 2 into, so integration of a1 square with dx, so this will be something like a1 square, so this will be x, this will be 0 to L, isn't it? Plus you have 4 times a1 multiplied by a2, so this x will become now x square divided by 2, and its limit is from 0 to L, plus 4 times a2 square, and this x square will become x to the power 3 divided by 3, and it has a limit from 0 to L. Okay, so if you solve this entire term, so your strain energy equation is going to become ae divided by 2. Okay, and this will be something like a1 square into L plus 4 times a1 a2 into, so this will be L to the power 2 divided by 2. Okay, so this 2 and this 2 will be slightly cancelled. Okay, some portion will be gone over here. So in place of this, so I'm going to write down over here this as 2. Okay, plus, so you have 4 by 3 now. Okay, and you have a 2 square, and this x square, x to the power 3 will become L to the power 3. Okay, so this is the expression. Let us call this as expression number 3. So this is the expression for the strain energy. Okay, now let us quickly go for the work done.
Throw 4 by 3.
Sorry, 4 by 3, my mistake. This is a 4 by 3. Okay, fine, thank you. So let us go for work done now. Okay, so work done, usually it is written by a symbol W, and here in our case only one term is there, so we are going to go for surface load. Integration over the surface u transpose fs into ds. Okay, so now our u, so we have already calculated the value of u, so let me write down, this is integration over the surface. So u we have calculated as a1 into x plus a2 into x square. Okay, and your surface force is defined by simple expression c into x, and this has to be integrated over ds. Okay, so now ds can be written as dx into 1. So this we have already seen, and if you use this, your integration over the surface will now become integration over the length, because the circumference portion we are considering this as a unity, that is 1. So the same expression now can be written as integration over the length. So if you go for the multiplication of these terms, so this will be a1 into c into x square, plus we have a2 into c into x to the power 3. Okay, and this will be integrated over the length now. Okay, that is dx. Okay, so if you go for the integration of this, so ultimately at the end, of course this will be negative because this is a work done, so I forgot to mention a negative sign. Okay, so if you go for the integration of this, so this will be something like a1 into c, so this x to x square integration will be x to the power 3 upon 3, so this will be L to the power 3 upon 3. Okay, minus you will have something like a c sorry, rather a2 into c. So x cube will be now x to the power 4 upon 4. So this will be divided by 4, and x to the power 4 will now become L to the power 4 over here. Okay, so this is your expression number 4. Okay, so this is how you can get the value of work done also, right? So now let us write down the total potential energy. Okay, so this is total potential energy is nothing but your strain energy plus work done, isn't it? So we have already calculated the equation for the strain energy as well as the total potential energy. So your strain energy and work done, sorry. So this pi is nothing but the strain energy. We have already calculated the value of strain energy as something like this, that is a e upon 2 into, this will be a1 square into L plus 2 times a1 a2 L square plus 4 by 3 times, sorry, this is a2, not a1. So this is a2 square L to the power 3. So this is your strain energy. Work done is negative. Okay, so negative will be something like a1 c L to the power 3 divided by 3 minus you have a2 c L to the power 4 divided by 4. So now for the first time you will find in the total potential energy there are two unknowns. Okay, so let us call this as expression number 5, and it has got two unknowns. Okay, these two unknowns are a1 and a2. Okay, so till now whatever problem we have solved, in that we are either having a1 or having a2, but this is both. Okay, both are present over here. So now in order to maintain the equilibrium, this total potential energy should be minimum, isn't it? So for this purpose, what we can do is we can go for a partial derivative. So d pi by d a1, this should be 0, and we have to go for d pi by d a2, this should also be 0. Okay, so now we have to derivative the total potential energy with respect to a1 as well as with respect to a2. Okay, so now let us go for d del pi by del a1 equals to 0. Okay, so here if you go for a derivative of this, so ultimately what you are going to get, this is a e upon 2, this is a constant. So here you will get a1 square. Okay, here you have to go for derivative with a1, so this will not be there. Okay, okay, let me write down one more time. So this L is a constant and this a1 square, so if you go for derivative of a1 square, so what you are going to get, 2 times a1. Okay, plus, so since we are going for derivative of a1, so if you go for derivative of a1 with this, so a1 will be gone, so this will be 2 times a2 L square. Okay, plus here there is no a1 term, so this will be 0. I hope this is clear. बराबर है ये? Okay, then if you go for this derivative of this a1 term, so this only a1 is over here, so this will be c L to the power 3 divided by 3. Okay, a1 will be gone and there is no a1 term in the second term, so this will be 0. Okay, and this will be equal to 0, right? So now if you rewrite this expression, what you are going to get is ae divided by 2 into, this is 2 times a1 into L plus 2 times a2 into L square. Okay, minus, so if I take this term over here, in that case, if you write down over here, so let me go for this, so this will be c L to the power 3 divided by 3. Okay, so you can even rearrange some of the terms over here, so you can take out this 2 outside. Okay, so if you take out this 2 outside, this 2 outside, so this will be completely gone. So if you rewrite this expression, so what you are going to get, this is something like A1 into L plus A2 into L square equals to, you have something like C L to the power 3 divided by 3 times A into E. Okay, so this is first expression. So I am going to call this as expression number A. Okay, now you can even let me undo this, because I can even go for more simplified way of this. So you can even take out this L outside. Okay, so ye L cut jayega, ye L cut jayega, and ye L cut jayega. So what you can rewrite this as A1 plus, sorry, I'm going slightly. Okay, so this is A2 into L square. So sorry, not L square, only L will be there, and this will be equals to C L to the power 2 divided by 3 times A into E. Okay, so let us call this as expression number A. So this is more simplified way, and this expression can be calculated by just taking a derivative of total potential energy with respect to A1. Okay, so now let us quickly go for the derivative of total potential energy with respect to now A2. Okay, so I'm just going for del pi by del A2, and this has to be equal to 0. Okay, so if you rewrite this expression, okay, so I have something like AE by 2 outside. So let me write down over here. So this is AE divided by 2 outside. Now remember, we are going for a derivative of the total potential energy with respect to A2. Okay, so here if you see in the first term there is no A2 term, so of course this will be 0 now. Okay, so this will be 0. Now the second term over here, only A2 is there. Okay, so A2, if you go for derivative, this will become 1. So this expression will become 2 A1 L square. So this is something like 2 A1 L square. Okay, so this is the second value. Okay, and the third value, we are going for derivative of this 2. So this A2 square will become 2 times A2, isn't it? So this is 4 by 3 into 2 times A2, it becomes 8 by 3 into A2 into L to the power 3. Okay, so this is 8 by 3, okay, into A2 into L to the power 3. Is it okay? बराबर है ये? Yes, students, is it okay?
Yes, sir.
Okay, then minus. Okay, we are going for a derivative of A2, so this will be 0. So of course this part will be 0. Minus, we have to go for derivative of this, so A2 will be gone, so all remaining is C L to the power 4 by 4. So this is something like C L to the power 4 divided by 4. Okay, so now we just have to rearrange some of the terms over here. Okay, and you can get the solution for this. Okay, so let me do that. So if you go for something like this is A E divided by 2. Okay, and here this is 2 times A1 L square plus this is 8 by 3 A2 L to the power cube. Okay, so this has to be equated to 0, so I am going for the transfer of this term over here. So this can be written as C L to the power 4 divided by 4. Okay, so here this 2 and some portion of this 2 will be gone. Okay, so I'm just going to rewrite the same term over here. So this is AE into this is A1 L square plus this will be now 4 by 3 A2 L to the power 3 equals to C L to the power 4 by 4. So I can delete this L term also from here and here. So the same expression now can be written as A into E into A1. Okay, so this is 4 upon 3 into A2 into L. Okay, so this is first term equals to C L to the power 2 divided by 4. Okay, so this is more simplified expression. Okay, so let us call this as expression number 2. Okay, so now we have two expressions, that is expression A and expression B, wherein we have two unknowns. Okay, so one unknown is over here, that is A1, and this is also A1, and second unknown is over here, so this is your A2. Okay, so this is a A2 over here. So we have two equations, we have two unknowns, so definitely yes, we can solve this particular expression. Okay, so let us do that. Okay, so let me write down this expression over here. So the A expression is something like this. So this is A1 plus A2 into L equals to CL square divided by 3 times AE. Okay, so in this expression I have to transfer this AE over here so that it becomes even more simplified. So expression B will become here as A1 plus 4 by 3 times A2 into L, and here you have C L square divided by 4 times AE, isn't it? So now you can easily solve this. So for solving this, I'll just deduct expression B from expression A. So this will become 0. Okay, and I think you can get this. This is this minus this. So 1 divided by 4 by 3. How much is that? Anybody? 1 divided by 4 by 3. Yes, I think it is minus 0.33. बराबर है? Yes, 1 divided by, sorry, 1 minus 4 by 3, that is 1 minus 1.33. So this will become minus 0.333, and this will be A2 into L. Okay, and of course this minus this. Okay, so you will get some value over here. Okay, so if you solve this, you will get the value of A2. Okay, so value of A2 is coming out to be minus this is 3CL divided by 12 times AE. Okay, somebody please cross check whether it is correct or not. I hope this is correct. And later on you can substitute the value of this A2 into either of this expression. You can substitute it in equation A or equation B, and then you can also get the value of A1. Okay, so A1 value is coming out to be 7 times CL square divided by 12 times AE. Yes, somebody please cross check this. Is it correct?
Correct, sir.
Correct, hai?
Yes, sir.
Fine. So remember our expression for displacement. Okay, so this was our expression for displacement, that is expression number 1. So expression number 1 was U equals to A1 into X plus A2 into X square. So now we know the value of unknowns A1 and A2. Okay, so let me rewrite the expression number 1 one more time. Okay, so this is my expression number 1. I am writing down one more time. So this is U equals to A1 into X. So this A1 is nothing but 7CL square divided by 12 times AE into X minus A2 into X square. Okay, sorry, A2 into X cube. I think this was the square term.
Square term.
Yeah. मैंने कुछ गड़बड़ किया है क्या? Yeah, this the A2 with the square term, right? So this is A2. The value of A2 is 3CL divided by 12 times AE into X square. Okay, so now this is the final value of the unknown displacement. Now let us plot the variation of displacement with the help of the equation which we have obtained. Okay, so for this purpose let me draw a simple line over here. Okay, so we have over here something like this is X equals to 0 and here X equals to L. Okay, so now in this expression, if you substitute this X and this X as 0, okay, so what will happen? Everything is going to become 0. So here the displacement at this point will be 0. Okay, Now if you substitute the value of x as L, okay, so here I'm going to put L over here. So what is going to happen? So here you are going to get something like 7CL cube, okay, divided by 12 times AE, minus here you are going to get 3CL cube one more time, because this is x square, so this will become L square, divided by 12 times AE. So if you solve this, so what you are going to get, this is 4 by 12, okay, 4 by 12 CL cube divided by AE. So 4 by 12 can be written as 1 by 3 also, okay. So let me write down over here 1 by 3, okay. So all you are going to get over here, there is a displacement
1/4.
1 by 4, sorry, 12 by 4 by 12 tha na? Okay, so this will be 1 by 4. Okay, so this is 1 by 4. Okay, so here you will be getting CL cube divided by 4 times AE. Okay, but now if you see the expression over here, so this is x and this is x cube, right? So this is a second degree polynomial. So what you can do is you can join this particular point not with the help of straight line but with the help of a curve, and your curve will be going like this. Okay, so this is what is expected, because you see the distribution of load is like this. At the support we have zero load, and as you move away from the support your load is continuously increasing. Okay, so accordingly the elongation will also increase proportionately. Okay, it will not be a straight line, it will be in form of a curve only. So here whatever displacement you are getting, we are getting it in a correct form. Okay, so now let us quickly go for the strains now. So your strain is nothing but du by dx. So here the value of du by dx can be calculated over here. So since this is x, okay, so du by dx will become now 1. So here you are going to get something like 7 times CL square divided by 12 times A into E, and here minus this is 3 by 12. Okay, so this is in place of 3 by 12 I'll write 1 by 4. So this is CL divided by 4E. In place of this x square, now you have 2 times x. Okay, so I'll write down x over here and I'll just erase this 4 and I'll just write 2 over here in place of this. Okay, so now you see here this is the expression for strain. Okay, let us try to plot the value of strain over here. Okay, oh sorry. Okay, so now here the value of x is basically 0. Okay, so in this expression if you substitute the value of x as 0, what you are going to get? You are going to get only this part. Okay, so at this level there will be a constant strain. Okay, and this constant strain, its value is something like 7 CL to the power 2 divided by 12 times AE. Okay, now if you substitute the value of x as, let us say, L over here. Okay, so what you are going to get, that is strain is 7 times C L square divided by 12 times AE, minus this will be C L square divided by 2 times AE. Okay, so in place of this 2, let me write down, if you multiply this by 6, so this will be 6 and this will be 12. So at the end what you are going to get, this is C L square divided by 12 times AE. Am I right? Barabar hai? Okay, so here at this point when your x equals to L, you are getting a smaller strain. Okay, so at this point strain value is something like C L to the power 2 divided by 12 times AE. Okay, so this is what is expected, and this is a simple straight line. Not this this is a simple straight line because here we have only one x term. Okay, so what you can do is you can simply draw a straight line from this point to this point. Okay, so you can see that as the x value is changing, your strain is reducing. Okay, so the maximum strain is there at the end, and if you move ahead towards the end of the beam, so you are going to get the lesser strain. Okay, and this was not there in the earlier case. So if you refer the earlier case, your strain was constant. Okay, and that should not be a constant, it should be continuously changing. Okay, so now we are getting the correct variation of strain when you are taking the different polynomial. Okay, now similarly you can also have the variation of stress also. So stress is simply strain multiplied by your modulus of elasticity. Okay, E. So the same expression will be there, only thing is E part will be now gone. So this is 7 CL square divided by 12 times A minus we have something like C L divided by 2 times A multiplied by X over here. Okay, so in this case also you will get a same variation. Okay, so you will get a straight line like this. Okay, and your variation will be again reducing. Okay, so it will keep on reducing like this. Okay, so here all we have to do is just multiply the value of strains with E. So here you are going to get 7 C L square divided by 12A. So E part will be gone, and here C L square divided by 12 times A. Okay, so as you move away from the support, your stress will be now reduced. Okay, so this is how you are going to get the correct solution as far as this numerical is concerned. Okay, or when you are going for the correct or higher order displacement polynomial. Okay, is it okay? Is there any questions as far as this part is concerned?
So C into L
Sorry,
cube upon 3 so maximum displacement
मैक्सिमम डिस्प्लेसमेंट क्या आएगा?
4 के जगह 3 आएगा सर.
ये वाला
हाँ वही.
ठीक है, इट्स अ स्मॉल थिंग, यू कैन चेंज दिस. ओके, 4 ही आएगा ना रे, 3 और 4 है ना, बराबर तो है. यस, आई थिंक इट इज करेक्ट. अच्छा, ये 3 minus 4 is 4 divided by 3. ओके ओके, या ओके ओके, सो दिस विल बी 3. ओके, नो इशू, कोई बात नहीं. सो दिस विल बी 3. So this is 3 and this is 3. Okay, fine. Okay, is there any questions apart from this? So do you agree with this variation of stress? बराबर दिख रहा है अभी ये? Yes, somebody please respond.
Yes sir.
ठीक है, so earlier if you take a simple polynomial you are going to get this variation, but if you take a higher order polynomial, in that case you are going to get this variation. Okay, now you can even solve this problem using even more higher order polynomial. Okay, so here I'll be a little bit quick. So I can have case 3 also. Okay, now in the case 3 what I can do is I can even go for even higher order polynomial. So here I can have something like u is equal to a0 plus a1 times x plus a2 times x square plus a3 into x to the power 3. Okay, so I have gone even one step further. Okay, so here you will have to first of all calculate what is the strain energy, then you calculate what is the work done, then you calculate what is the total potential energy. Then you may happen that this total potential energy, that is pi, may be having a1 term, a2 term as well as a3 term. Okay, so if this is there, in that case you have to go for del pi by del a1 equals to 0. Okay, then we have to go for d pi by d a2 equals to 0, and then we may have to go for d pi by dA3 equals to 0. So if you do this, you are going to get 3 equations. Okay, having 3 unknowns a1, a2 and a3. You solve this. Okay, so if you solve this, what you are going to get, the a1 value you will get, a2 value you will get, you will also get the a3 value. Okay, so once you know the value of a1, a2, a3, of course this a0 will be 0, so you can substitute these values in this expression. Okay, so finally your this u value is going to become something like this. Okay, let me just write down the values over here. So the final expression for u will be something like c divided by 6 times ea multiplied by, you have 3l square into x minus x to the power 3. Okay, so now here if you try to plot a graph, okay, so here if you try to plot a graph, it will come something like this only. Okay, so here the variation of this displacement is like this. Okay, so here it is going like this. So slowly it is going up, and it will go like this. Okay, so this is the variation of the displacement which you will get. Okay, and then if you go for the derivative of this u with x, so you are going to get the strain component. So strain is nothing but du by dx, and its value will be something like c divided by 6 times e into a multiplied by, this will be 3 times l square minus 3 times x square. Okay, and you will get a similar kind of a variation which we have obtained earlier, but earlier it was a straight line. Okay, so if you remember, this was a straight line, but now in place of straight line you are going to get a simple curve. Okay, so your curve will be like this. Okay, so you will have the higher values over here, and slowly this value are now going down with the help of a curve, and you will get a some value over here. This is a strain value, right? Similarly, you can also get the stress value. So stress can be calculated as strain multiplied by modulus of elasticity. Okay, so here is a cross sign, so the same expression will come over here without e. Okay, so this is c divided by 6 into a multiplied by 3l square minus 3x square. Okay, so now here you will have a similar kind of expression. Okay, so let me draw a curve like this. Okay, here you will also get a straight line like this, and here again it is reducing slightly down. Okay, so this is the variation of the stress. Okay, so you see 3 figures. Okay, so this is the first figure. Okay, so this is the first figure. So strain is increasing, strain is constant. Sorry, the displacement is increasing, the strain is constant, stress is also constant. But here if you see, the displacement is increasing but the order is more. The stress is stress and strain both are reducing but of first order, but in this case the displacement is of second order, and the strain and stress, it is of the one order less. Okay, so this is how the problem can be solved if you go for third degree polynomial, which is over here. This is the case 3. Okay, I hope this is clear to you. Okay, is there any queries as far as this part is concerned? Yes. Okay, so we are done with the problem today. Okay, so if you have any doubts, please remain in the meet, otherwise you can leave the meet. I am stopping the recording now.